Hello, students. So today's class we will be discussing about a technique that is used to write repetitive algorithms, and the use of a stack won't be very evident initially, but as we'll see later that this concept actually uses a stack for implementation. So the concept that we are going to discuss today is something that you already know from your programming classes. It's called recursion. And there are basically two ways of writing any repetitive algorithm. One is to use loops, like you can use a for loop or any of the loops. That is known as an iterative or iteration approach. And the other one to write repetitive algorithm, the other approach is called recursion. So today we'll have a look at recursive techniques or how to write a recursive program. And later on, we'll try to understand how recursion actually uses a stack to do whatever it does. So what is recursion? Recursion is, by definition, whenever a function calls itself, it's known as a recursive definition. So let me just write it down. Whenever a function definition calls itself, it is known as a recursive definition. Before we go with program and all, let's try to take one example which uses recursion. So it's a very common example, factorial of a number. Factorial of a number. Now, what is factorial of a number? You know, if it's like 4 factorial, it will be 4 into 3 into 2 into 1, right? Now, what is so recursive about this? The thing is, this is what we know, like in math and all, this is how we compute a factorial. But if we think about it, actual implementation, like if you were to write a program for this, of course, you can go for an iterative version for the same computation of a factorial, but the recursive one is more natural. Let me show you what I mean. So it's like 4 factorial is actually 4 into 3 factorial. Okay, so to compute 4 factorial, you will need to compute 3 factorial also. So what is 3 factorial? Same, 3 into 1 less 2 factorial. To compute 2 factorial, you will need to compute 1 factorial. What is 1 factorial? 1 factorial is 1 into 0 factorial. Now, it's a fact that 0 factorial is actually equal to 1. Okay, so 0 factorial is 1. Now, see, this is where this recursive thing will stop. This is all recursion. When you are trying to compute 4 factorial, you end up computing 3 factorial. Okay, to compute 3 factorial, you will have to know how to compute 2 factorial. So basically, you are trying to compute a factorial and you end up computing another factorial. So this is exactly what recursion means. So if we go along with the flow, 1 factorial will be 1 into 0 factorial. Now 0 factorial won't have anything like minus 1 into, or 0 factorial won't have anything like 0 into minus 1 factorial. It's not like that. It's a known fact that 0 factorial is equal to 1. So this is where we stop. Recursion stops here. Now once the recursion stops, what happens? We need to go back. We need to backtrack. Okay, what do I mean by that? Once you know that 0 factorial is equal to 1 and you know there's no recursive computation of some other number factorial, you need to go back to the previous step, because we ended up in this step only because we were here. Okay, or you can say if you start from from here, 4 factorial is 4 into 3 factorial. This computation is not yet complete, because unless we know what is the value of 3 factorial, we will not know what is 4 factorial. So to compute 3 factorial, you will again end up with another recursive function or recursive computation, whatever. That is 3 factorial is 3 into 2 factorial. Again, we don't know the answer. And that's how we, ended up in this line. This is like the end of the recursive call. So 0 factorial is 1. So now we are going to use this value in the previous step. So what will happen now? 0 factorial, which was in the previous line, will be replaced with this value because 0 factorial is 1. So 1 factorial is now 1 into 1. That is 1. Once you know what is the value of 1 factorial, you need to go back to the previous line. Okay, so this 1 factorial will have the value 1, which is coming from this line. And this will give us 2 factorial is equal to 2 into 1. That is 2. And now we also know what is the value of 2 factorial. That is 2. Once you know this, you can use this value in the previous step. So 3 factorial is 3 into 2 factorial. Now what is 2 factorial? We already know the answer. By backtracking, we know 2 factorial is actually 2. So 3 factorial will be 3 into 2. That is 6. Now that we know the value of 3 factorial, we just have to replace that, substitute that value in the previous line. So 4 factorial will be 4 into 3 factorial, which is 6. And 4 into 6 will be, 4 times 6 will be 24. And this is how we actually get the value of 4 factorial. So even though we do it like this, 4 into 3 into 2 into 1, which is okay, but the way it actually is done or implemented, if you were to use recursion, is like this. Okay? So basically what you have to understand here is there are 2 things. What is recursion? Okay? Don't worry about programs and all. What is recursion? Intuitively, what is recursion? So recursion is an operation that when you are trying to do an operation like 4 factorial, you end up doing another factorial operation. Okay, of course, it will be for a smaller number, right? And likewise, for 3 factorial, you will be computing the factorial of 2, which is smaller than 3. So you go on like this, and eventually your recursion will end. Okay, this is known as a base case or trivial case, which is actually very important because if there were no base cases or trivial cases in a recursive call, the recursive call will become an infinite thing, right? It will never stop, which is not good, right? Any infinite recursive call or any infinite iterative call is not good unless you want it to be infinite. Like I think I have given a few examples in some of the previous classes. For example, if you are writing developing an app for a server, okay, and server keeps waiting for requests from clients, okay, then you will have to write a code which is infinite in nature because it has to keep waiting for requests from the client. Okay, so there are situations like that when you would like to go for something infinite, but usually the case is we do not encourage or we would not like to have recursive or iterative infinite calls because that will mean that it will end up consuming all the resources in the computer. Okay, so the good thing about every recursive call is there will always be a base case. You have to know what is the base case. Okay, you have to know what is the trivial case. What is the base case? It's that situation when the recursion finally stops. You cannot go beyond that. For example, 0 factorial. If you're computing the factorial of any number, it could be any number. It may not be 4 factorial. It can be a big number. But eventually, it will come down to 0 factorial, which will be equal to 1. And, you won't go beyond that. So that's when your recursion stops. Recursion has to stop sometime. And once the recursion stops at the base case, whatever value you get in the base case, that has to be given back to the previous steps. And eventually you end up with the actual answer. So two things. What is recursion? Hopefully it's clear. And why do we need a base case? Or what exactly is a base case? I hope these two things are clear. So how do we write this? Mathematically, this is how you can write this. So to compute n factorial is 1 if n is equal to 0. Okay, like this is n, no? This is n. So if n is equal to 0, it is 1. Fine. Otherwise, it will be, you look at this. If this is n, what is this? If this is n factorial, this will be n into n minus 1 factorial, right? This is 4, n is 4, right? So 4 minus 1 will be 3 factorial. So this is what you need to write. N into n minus 1 factorial if n is greater than 0. So this part, the second statement, this is the recursive definition, because while trying to compute factorial of some number n, you end up doing the same operation, that is another factorial operation. Of course, not for n only, it will be n minus 1, but it still is a recursive operation, right? It's the same factorial operation. So with this much of understanding, let us write the program for this. I'll not type the program because it's a very common program. You can type it yourself. You will have to write the main and all for this. Now, if we were to write a C program for this, okay, let's write a C program. I'm just writing the function definition, okay? I'm not writing the entire program. So you will need to have a main. You'll have to declare the function and all, right? So those things you should be able to do by now. Okay, so how do we compute a factorial? Now, if you have followed the algorithm that, or the definition that I just wrote, yes, this one, okay. What is the first line? If n is equal to 0, then n factorial will be 1. That is obviously the base case, right? So base case is what you have to write first. So we say if n is equal to, because this is the program, you have to write equal to twice. So if n is equal to 0, then factorial will be what? 1, no? You see the return type here int. I'll just say return 1. Okay. Make sure you understand this line. This is the base case. These two lines are for the base case. This one. If n is equal to 0, n factorial will be 1. So we don't say n factorial will be 1. We'll just say return 1. Base case. Otherwise, what is the next one? If n is not equal to 0, if it's greater than 0, it won't be less than 0, obviously, right? Because at 0 it is stopped. If it's greater than 0, like it can be any number, like 1 or 2 or 3 or anything. What we have to do is we have to go for a recursive definition. What is the recursive definition? You have to multiply n, whatever n you have, with 1 less than that value of n. And, of course, the factorial of that. So n into n minus 1 factorial. So how do we write this? If n is equal to 0, return 1. Else, you don't have to write else because there's a return statement here. So we have to do n into n minus 1. So what I will do is, I'll use x here, right? X is n minus 1. Y will be factorial of x. See, let me rewrite it again. N factorial is 1 if n is equal to 0. This we have already done, right? This is this part. It's n into n minus 1 factorial if n is greater than 0. So this n minus 1 factorial is what we are doing here. This y is actually factorial of x. What is x? X is n minus 1. So this one we are computing first, and then we are going to multiply that value with Okay, that's it. So this is your function definition for a factorial operation. Now you see the recursion is here. This line is the recursive line. So going back to the first line, whenever a function definition calls itself within the function itself, it is known as a recursive definition. So what is the function definition here? It's fact, no? We are inside the function fact. And inside the function, you see the function is calling itself. Of course, with a different argument, x is basically n minus 1, but it is calling itself. So basically what will happen is, once you reach this line, it will go out of the function and go back to the beginning of this. Of course, with a different value in the argument, it will be whatever was n, it will be n minus 1. And this keeps happening until you reach the base case, as explained in the previous example, and then you start tracing back. Now, how exactly all these things uses the stack and all, we'll learn in a moment. But for now, make sure you understand the program. Okay, it's directly written from the algorithm, not the algorithm, from the definition that we have for a factorial of any number. Okay, and please remember that this is the recursive call. Recursive call. Okay, function name, same. So within the same function, you have a line or a statement calling the function again itself. So recursion, as I always tell in the class, you have a very good movie based. It's not really based on recursion, but it's very similar to recursion. So it's the movie is Inception. If you have seen the movie, good. If you haven't seen the movie, then also it's fine. But it's a really good movie, and you can actually watch this. So the actor is of course Leonardo, the Titanic hero. Okay, and the movie is actually very nice. You have, you can go to sleep, and in your sleep you go to your dream, and in your dreams you can go to another level of dreams. So you have basically multiple levels of dreams where you can go and make changes in your past or whatever, right? Like you can manipulate your life and all. So that's the movie. It's a very nice movie where you have different levels of dreams, and you can keep going deeper and deeper into those levels. But there comes a time when your level, the depth of your dreams to which you are going into, that needs to be stopped. Okay, so there's a small instrument. It's a small, like it's like a top that you can spin. Like it's like a spinner. Okay, so when that thing spins in your dream, or when you can spin that spinner in your dream, then your dream stops. Your dream at that level stops, and that is akin or similar to your base case in a recursive call. So please go ahead and watch the movie Inception. That will give you a different perspective of what recursion is. Of course, you don't need to watch the movie to understand recursion, but just in case, if you are willing to watch till some time with a good movie, you can go and watch Inception. Okay, so with this done, now let's try to understand how exactly this multiple recursive calls, works, because this is where we will have to bring in stack without having an understanding of the stack, which you already have. Don't worry. You will not really understand how a recursion or a recursive function call actually works. So keep this with you. Okay, just write it down. Pause the video here. Write this program and keep it beside you when I'm discussing the example in the next page. So the way recursion actually works is recursive calls no, let me rewrite. I'll just write it down so that it's easier for you to take notes. Every time a recursive call is made, what is the meaning of this? Every time, you are in the factorial function, and inside that, you remember this line, no? This line. So you're inside this. So you, like, n is 4 initially. So you go to the function with n equal to 4. You do this, and here x is basically n minus 1, that is 4 minus 1, 3. And with this recursive call, you go back to the same function, and this one is 3. Okay? So initially it was 4, and you never reached the last line. You see, when n was 4, you never reached the last line. So that function is actually incomplete. And before you can finish that, you have to finish factorial of 3. You go out again and do the same thing, and you get stuck again. And this time n will be 2. Just the way we have done in the example here. Okay, so the function doesn't, really complete itself until it reaches the base case, and things are backtracked to get the complete answer. So what this means is every recursive call means a new set of variables like x, y, and this n. There will be a separate set of values for n, x, and y for this particular example. Okay, like if it's some different recursive function, and obviously that will have a different set of variables. So you will have multiple copies of those variables again. So coming back to our program, because we have 3 variables, n, x, and y, every time there is a recursive call, okay, and the function comes out of the control comes out of function and goes back to the function again itself. That's the recursion is. And you start with a different set of variables again. You keep doing this until you reach the base case. Base case is this one, at which something happens, and the answer starts flowing in. So that is what we will try to understand, how exactly it happens in a computer. So going back to the notes, every time recursive call is made, a new set of variables is allocated and used. So for our case, it will be n, x, and y. So there will be multiple values of n, x, and y. There will be different instances. It's called instances. Okay, so you will have multiple copies. So if you can see through the entire thing, you will see that there are different values of n, different values of x, different values of y. Okay, so I will just write it down, multiple instances. So what this means is every time a recursive call is made, a new set of variables is allocated and used. So what happens to the old one? So they will be inactive for that moment. Okay. So whenever you make a recursive call, let me go back. So let's say we started with n equal to 4. So n was 4. Then inside this, you have n is not equal to 0. So you come down to this. So x is n minus 1. That is 4 minus 1. X is 3. Right. And then you go to the next line. Y is assigned. Now that's where you get stuck, because this is factorial of 3. So you basically come out of the function and go back to this again. So what will happen? Now n will be, because this is a new instance, n will be now 3. And because n is not equal to 0, you will come down here again. X will be 3 minus 1, 2. And y will be factorial of 2. And you get stuck again. I hope you're getting the picture, right? So these are the different instances. So basically, when you were here, these things were active. But as soon as you end up with a recursive call, and you have a different set of variables, new set of variables, the same one, but with different values, this part becomes inactive. Whatever you have right now will be active, and you will be working on that. But as you can see, because of this recursive call, it will go back to the same function again, and this time n will be 2, x will be 1, y will be factorial of 1, and again another recursive call, and so on. So I hope you're getting the picture. Basically, these are different instances, and only one of them will be active. So does this remind you of a stack? See, first set of variables was the was pushed on the stack, okay? And then there was a recursive call, and you get another set of variables. This one is pushed to the stack top. So this one goes in. So it has become a little reversed. So it would like this one should have I could have written it here, right? So you can think of it like this. So basically, you are looking at a stack where you have a value of n. Let me write it. So n is um, okay. So n is I'm writing this, okay. N is 4, x is 3, and y is not yet computed. So let me just put a star. And with this, because this is a recursive call, you go back to the same function, recursive function, and you end up with another set of variables. So basically, those new set of variables, you can just think of them as getting pushed to the stack top. I hope you're getting the point. And if you just try to visualize this, this is nothing but a stack. So you had something here originally, and then you put something on the top of that, those variables. So right now, this is the stack top. And if you remember, on a stack, only the top variables are visible, only those are accessible. Anything beneath those variables, you cannot really see. Okay. So every instance that we get during a recursive call, you can think of those as stack elements. Okay. Different stack elements are being pushed or added rather to the stack. And similarly, you can have you can think of this as 2, 1, and I'm putting a star because it's not yet complete. So if this representation is clear, I will use this one um, right now to actually explain you how a recursive call actually works. Okay, but before that, make sure you understand why we are bringing in the stack, because what we see right now is a stack. This is a stack. And by the way, this stack is not one that we wrote. It's a stack that is already available in a computer in the operating system. Okay, so it's called a call stack. So it's an inbuilt stack in every operating system. Okay, so whenever you have recursive function calls, or even when you are passing a normal function parameters, those times you use a call stack. There are other uses of call stack. For example, when you declare variables like int x and y, okay, need not be within a function, just normal variables. Those will also go into a stack. And whenever you have a stack, you have push and pop operations, right? That is very clear to us because we have been doing that for quite some time now. Okay, now let's try to understand how this stack is being used to get the answer 24, right? The answer was 24, right? Yes. So let's try to understand this. So again, I'll say, I hope all of you have written this down. Keep it with you. And remember that we're going to use a stack like this. And I'll try to explain the code. Okay. I'll just write it down. Okay. Use as a call stack. Now, if you want to know more about what is a call stack, you will have to go to your course, that is computer architecture, okay, or even microprocessor will do. So you have something called a stack pointer, which actually points to the current stack element, the top one. So there is a stack, built-in stack in every microprocessor. So you just have to know that that stack is only being used by these function calls and recursive function calls. Okay. Okay, now let's try to understand this example. So for example, if I have printf factorial of some factorial of 4. Okay, this is in the main function, okay, which I didn't write, by the way. So how will this work? So let's first try to draw the stack. So this is the stack. Okay, I'm putting partitions here. In real life, there won't be any partitions, but I'm putting partitions because it will be easier for you to understand. So in the memory, you will have a space for n, x, and y. Okay, so initially this is the initial stage where all these things are empty. Now make sure you are looking at the program. So just for once, I will go back to the program. So now, because we are doing fact 4, okay, so we have passed 4 to the function. So where is it getting passed? It's getting passed to n, right? 4 is basically, n will be having the value 4. So when we say fact 4, what will happen? So, the value 4 will be stored here, and what about x? Initially, there won't be any value because this is the first time that the function is being called. Okay, so this is how your stack will look like. Okay, then n is 4, right? Now we have x and y. X and y, there are no values as such, so that's why I put a star there. This one, because they are uninitialized right now, so that's why I put a star there. Okay. Next, we check if n is equal to 0. No, n is equal to 4, right? So this line will not be executed. So we go to the next line. What is there in the next line? It says x should be assigned n minus 1. Okay, so let's do that. X should be assigned n minus 1. So I'm getting kind of mixed up with the colors here. I hope you can understand. So n is 4 from the previous function call, and because now we're inside the function, x has just been computed as n minus 1. So x is 3. What about y? It's still star. Done. This line is done. Then we have y is assigned factorial of x. Now you see this is a recursive call. So y will not have any value as such, but because of this line, we will end up with a recursive call. So we are going to go back to the beginning of the function, but this time n will have a different value, that is 3. So how do we write that here? So now n will have 3 star star. Just the way we started with this for fact 4. Now in the process, like when we were inside the function with n equal to 4, we ended up with the value of x equal to 3, and y is still a star, it's unknown. But at the same time, that line, this line here, the recursive line, made us go back to the beginning of the function again, but with a different value. So with that recursive call will create a new instance, okay, of variables. This one that I had shown you before, or here you can see here, okay. So this is basically using a stack. So you can think of this as this was the first set of elements, and now the first recursive call fact3, okay, it pushed in a different set of variables. So this is the stack top right now. Okay, this was the stack top initially. Initially, the stack top was empty, obviously, right? And then we had this new set of variables for fact 4, and for fact 3 we have another set of variables. And when you have these values like n n equal to 4, x equal to 3, and all these become hidden, right? Because that is the nature of any stack. You can only see or access the top element. So what is there on the top? N equal to 3, x is undefined, y is undefined. Okay, which is not a problem, but what you need to understand is these values are the only values that are visible and accessible right now. Okay, so we are using a stack, and what we did just now is a push operation. So I will just write it down. We just pushed in 3 star star to the stack top. Okay, here also this was a push operation. I didn't really mention that explicitly, but I hope you understand that. Okay, next one. So now we have n equal to 3. Let's go back to the function. Before that, let me just write down the existing values. 4, 3 star. Okay, 3. Okay, now I will not put a star here because we are basically at fact 3, no? So fact 3 means n is equal to 3 now. Okay, so initially x and y are uninitialized, so we put a star star there, and then we check, is n equal to 0? No, n is equal to 3. So this line will not be executed. We are now here. So now we are going to get a value for x. What is x? X is n minus 1. 3 minus 1, that is 2. So let's go back to our stack and put a 2 here. Okay, go back. Done. Now let's go to the next one. Y is assigned factorial of x. Again, it's a recursive function. We are going to get stuck again, which is not a problem because that's how recursion works. But this basically means that what will be, sorry, I should not have put that. Anyway, fact of x will be, what is x? X is now 2. So this time we will be going back with fact of 2. Okay, so let's go back here. So y is undefined, and just now we ended up with another recursive call with n equal to 2. So we have this here. Done. Okay, so this right now is the stack top. And we have a lot of other elements below this, but again, because it's a stack, we don't know what elements are there. Only one set of elements or one instance will be active. Right. Next, let's continue with this. So now n is equal to 2. Okay. Okay. So n is equal to 2. Let's go back. So now, because this is, we're going back here. So now n is equal to 2. So that will give us so here, let me write down the previous content. This is 4, 3 star, 3, 2 star, and we had 2 here, and it's star star from the previous one. But because now we are inside the function, I'm not going to the program again. You just go through that. The x and y initially are uninitialized, and then we check, is n equal to 0? No, n is equal to 2. So we will go to the next line, that is x is assigned n minus 1. So what is n minus 1? 2 minus 1 will be 1. That will be assigned to x. Done. Then we go to the next line, that is y is assigned factorial of x. Factorial of x means factorial of 1. So again, another recursive call, meaning another new set of variables are going to come in. So let me write it down. We start with 1 star star. You see, I hope all of you have got the flow by now. So what is this? This is factorial of 1. Okay. And then, because it's a recursive call, we go back to the function again. Let me draw the stack again. So it's a little bit time taking, but once we are done with this, you will have a solid understanding of how recursion actually uses the stack and how recursion actually works. Okay. So let me fill up from the previous content. 4, 3 star, 3, 2 star, 2, 1 star, 1. Yeah, let's stop there. Okay, let's go back. So now we have factorial 1. Okay, so n is equal to 1 now. So n is equal to 1, and we check is n equal to 0? No. So we go for the next line. X is assigned n minus 1. What is n? N is 1. 1 minus 1 will be 0. Okay, let's go and fill it up. X is now 0. And then we go to the next line. Y is factorial of 0. Another recursive call. So y will be undefined, but at the same time we will have, because it's a recursive call, a new set of variables will be created. So we will have 0 star target. Okay. So what is this actually? This is factorial of 0. Done? Okay. This is the stack top. And a lot of other variables are there. We don't really see them. Now factorial 0, let's go back to the program. We're almost at the end of it. So this is factorial of 0. So now we are going in with the value of 0, right? N is equal to 0 now. So yeah, let me draw the stack first. N, X, Y. Fill up the previous values. 4, 3 star, 3, 2 star, 2, 1 star, 1, 0 star, and 1, 0 star. Okay. And then we are at factorial of 1, factorial of 0, right? Let's go back to the code and see what happens. Now when you go here to this line, is n equal to 0? Yes, n is equal to 0. What is the next line? What does the next line say? It says return 1. Now there are two things going to happen. First is the value 1, the number 1 will be returned. Returned to which one? To the previous instance. Okay, let's get this very clear. Whenever you say return, inside any function, it may not be a recursive function. We have written many functions by now, isn't it? Think of all the programs we have done. There's always a return statement. So whenever there's a return statement, what happens? All the variables, local variables, are erased from the memory. Yeah, that is what I used to tell you. Basically, all the variables that were written on the stack. Okay, every function call uses a stack. Now you should be knowing this. So all the function variables used in the function will be cleared from the stack. Okay, so that is the first meaning of return. What I want to tell you is this: 0 star star, all these will now be removed from the stack. So the stack top will not be this anymore. This is going to be the top. Is this clear? Return means you are completely going to come out of this instance. You are going to erase or remove or delete all these ones. Okay, that's one meaning. And second is, it says return 1. So come out and return 1. Return 1 to whom? You have to keep track of what was happening, okay? So before n was 0, we were at n equal to 1, no? And we got stuck here, right, in this recursive call. So it was fact 0. So when we say return 1, this fact 0 will be substituted, or it will have this right hand side of this statement will have 1. That is the meaning of return some value. So we say return 1, no? So that return 1 goes to the previous instance of this recursive call where we were stuck, which is basically this, this line inside the red box. And basically fact 0 was where we had got stuck. So this, whatever is being returned, will be overwriting this place. The fact of 0 will have 1, and that 1 will be assigned to y. To sum it up, what is going to happen is, in the next line, in this line, y just got the value that was returned. That is, I'll use red for that, okay? This will have 1. Is it okay? And now, because you got 1, let's go back to the previous program. We are at fact of 1, okay? Because fact of 0 has already returned 1. So we are just back to the previous instance, okay? Not to the original one when n was equal to 4. The n is actually equal to 1. That's where we had got stuck. So you just got y equal to 1, right? We have just updated that on the stack also. So we are kind of done with this line, right? For this instance where n was equal to 1, we have got x equal to 0 and y equal to 1. Now we continue, right? Because see, we were stuck. We were stuck so many times in this line. So for this instance of fact 1, now we go to this last line. What does it say? Again, return. And you now know what is the meaning of return. Return means those variables that you have right now on the stack top will be cleared off, and whatever is the value, that will be given to the previous instance where you were stuck. See, this is a little bit complex in the sense if you lose the flow, you will not really understand. You might not understand what I'm trying to say. But please remember that there are multiple copies of the same function. Okay, because we were getting stuck many times. So we say return n. What is n? N is 1 into y. What is y? We just got y, 1. So return 1 into 1 is 1. Return 1. To whom? To this line of fact 2. Because you were in fact 1 only when you got stuck in this line when n was equal to 2. We are retracing back our steps. Okay? So when we say return 1 from this line, we are basically going back here when n was equal to 2. So in the next line, in the next instance, what is going to happen is 4, 3 star, 3, 2 star, and this will be 2, 1. This whole thing will be removed because we just say return, and whatever is the value n into 1, 1 into 1, that will be returned and basically substituted to y of fact of 2. Okay, so this is the stack top right now. So let me just write, this will be y equal to fact of 0. This will y equal to fact of 1. Yeah, because that is when we are actually returning these things. Okay. And if you have understood till here, same thing will be happening, right? So 4, 3 star, 3, 2, and this time n into 1 again. For the previous instance, when fact of 2 was called, n equal to 2. So 2 into 1, this line, the last line, n into y. N is 2 and y is 1. You see, n is 2 and y is 1. So 2 into 1 is 2. That will be returned to this place. Okay. Okay, I've run out of space, so I will write here. Okay, don't get confused. So we are almost done with this. This is 322. So we had 4, 3 star, and this is 322, right? So of course things are going to change now. So now n is equal to 3. So this is basically 3. N was 3. Okay, n was 3. and we are done here. So what do we have here? We have y is 2, y is 2, right? Y is 2 here, and n is 3. So once you have n and y, you will be going to the next line, that is return n into y. So 3 into 2 will be 6. So where will it get returned to? It will get returned to factorial of 4. So you see, we are almost at the starting point of the program. So 3 into 2, 6 will now be replacing this star here. So now y will have a value. So you can write this as y is factor of 3. Okay, done. And now we are in the starting position. Let us go back to. So we are at the place where we got stuck for the very first time when n was 4. Okay, and we didn't know what was y, because for that we have to compute factorial of 3, which we have already got. Okay, so y is now 6. So now next you go to the next line, right? This is for factorial of 4. Fine, n is equal to 4. N is equal to 4. So return n into y. N is 4, y is 6. That is 24. So what's going to happen? Return means what? Two things. You will be returning the value, and n into y, that is 4 into 6. 24 will be returned, and at the same time, all these things will be removed from the stack. So this is the final picture. The stack will be entirely empty now, because 4 into 6 will be popped out. Okay, 24 will be popped out, and it will be returned to which one? Where did we start actually? You see here. So this fact 4 will now be, will have the value 24, and that is what this printf statement will print on the screen. So this, you can write this as k printf %d factorial of 4. Okay, so you won't see 24 here, you will rather see 24 on the screen, and you see, just go through the stack. We were pushing here, and then we started popping out, pop, one last time. This was push. You see, we are actually using a stack. It's a call stack. It's not our stack. It's a stack already available in the operating system, in all the operating systems. And but we are using the push and pop operation, right? So we don't explicitly use push and pop. All those things are done implicitly by the OS, but basically that shows that we are actually using a stack and its operations, push and pop. So to wind up this lecture, in today's class you understood what is recursion and what are the conditions required to run or write any recursive function. You need to have a base case where you will stop the recursion, right? And then we understood how actually a call stack is used by any recursive function to actually compute the values that it's supposed to do. Okay, so this took us some time, but hopefully all of you have actually understood the role of a stack in recursive calls. Okay, apart from recursive calls, like I told you, any normal function call also uses a stack. Also, your local variable declarations also use a stack. So whenever you come out of a function, I told you many times before in the previous classes that whenever you come out of a function, all its local variables are deleted. Now, those are not really deleted, those are popped out from the call stack. Okay, so whichever way you understand, it's fine, but please remember that there is a stack, there is a built-in stack, and we actually use that for function definition, for recursive function calls, and also for local variable declaration. Okay, so just keep these points in your mind, And we will have one more class on this using recursion. That will be a very short class, so that I will maybe do tomorrow, and then we should be done with the stack chapter. Okay, then. So take your time, go through the lecture again if you need to understand things properly, and yeah, do ask questions if you have any doubt. Okay, then. Until next class, take care.